Now let's solve trigonometric equations that are a little bit more complicated than what we've seen so far. This first one says to find all possible exact solutions for the number 4 times the sine squared x minus 2 equals 0, where x is in radians and the angle x is between 0 and 2 pi. All right, so let me start by writing this one down. So I've got 4 times sine squared x minus 2 equals 0. Now my first step always is I want to get the x by itself. That's true not only in a trigonometric equation, but really in any algebraic equation. You got to get the x by itself. And right now that x is trapped inside that function. So before I can do anything, let's get that sine squared x by itself. So I'm going to add 2 to both sides, and then I'm going to divide by 4. So that's going to leave me with sine squared x equals 1/2. Now to get the x by itself, I'm going to square root both sides, and that's going to get me that the sine of x is equal to plus or minus the square root of 1/2. All right, so what I'm looking for, and let me maybe just simplify this a little bit. What is the square root of 1/2? The square root of 1/2 is plus or minus, well, the square root of 1 is 1, and the square root of 2 is the square root of 2. Now, whenever I have a radical in the denominator, I want to rationalize that denominator, so I'm going to actually call this plus or minus square root of 2 over 2. So what I'm looking for is the angle x. What angle, when I take the sine, gets me an angle measure of plus or minus the square root of 2 over 2. So let's go ahead and say sine inverse of the sine of x is equal to sine inverse of not only positive square root of 2 over 2, but also negative. And what I know is that that's going to happen at pi over 4. That's going to happen at 3 pi over 4. That's going to happen at, where else? 5 pi over 4. And that's going to happen at 7 pi over 4. So I'm going to write my final solution set with those 4 radian measures. Do I have to worry about writing plus 2 pi k where k is an integer? I do not, because I have all the solutions within 0 to 2 pi. Now, for part B, we'll notice right off the bat that there is no such limitation as there was on part A, right? That doesn't exist for part B. So in this case, we are going to be adding multiples of the period. Now, before I do anything else, let's just talk about what has happened to the period of this function. We've learned in other sections that in the inside of the argument of a trigonometric function is this number. If there's a number connected to the angle measure, that affects the period. So right off the bat, I can tell that the period of this function has changed. It has changed from 2 pi to now being 2 pi over that b value, or omega value, or whatever is on the inside of the parentheses. So for us, that's going to be 2 pi over 3. So that's important because when I go to write that plus 2 pi k, where k is an integer, I'm going to actually write plus 2 pi over 3 plus 2 pi over 3k, where k is an integer. Okay, so let's give this one a try. We're going to start out with cosine of 3 theta equals negative square root of 2 over 2. And I'm going to take cosine inverse of the left, and I'm going to take cosine inverse of the right. All right, so cosine inverse and the cosine undo each other, and I'm left with 3 theta is equal to, all right, what angle measure produces a cosine of negative square root of 2 over 2? Well, I think that happens at 3 pi over 4, but it also happens at 5 pi over 4, doesn't it? Okay, so now I'm going to have to divide by 3 to get the theta by itself. And I think on the left I'll divide by 3, but on the right with that fraction, maybe I will multiply by 1/3. I think that might make it easier. And so I get a theta value of, looks like 3 pi over 12, which is pi over 4. And also theta equals 5 pi over 12, which does not reduce. Okay, so those are the two solutions, but because it wants all of the possible solutions, I am going to add multiples of the period. So plus 2 pi over 3k plus 2 pi over 3k, where k is an integer. So you have to be maybe a little bit aware of anything that is affecting the period, and that thing is going to be some number that's connected to your angle measure. Let's look at some more examples. Part C. Find all possible exact solutions for 2x squared plus x equals 1. And Part D. Find all possible exact solutions for 2 times cosine of x squared plus the cosine of x equals 1. Now, Part C is not a trigonometric equation, but there are similarities between what the equation is in Part C and what the equation is in Part D. So what I want to point out to you here is that the rules that you use for solving algebraic equations are the same rules that you can use for solving trigonometric equations. So if you're struggling, you might consider thinking of it a little bit differently. Let me show you what I mean. So the equation we're being asked to solve is 2x squared plus x equals 1. Let's write that down. 2x squared plus x equals 1. And to solve, we're going to set everything equal to 0, which means that we need to subtract 1 from each side. Once it's set equal to 0, in order to solve this quadratic equation, we either need to try factoring, or we can use the quadratic formula. I'm hopeful that this one factors, so let me give it a try. If you are a little rusty with factoring, I would suggest that you just do some review on your own, maybe do a Google search of factoring, and I know you'll find tons of information. But what I know here is that the numbers that go in the first two slots have to be 2x and x. That's the only thing that multiplies to 2x squared. On the end, I need that product to end up equaling -1. So I'm going to use -1, 2x minus 1, and x plus 1. And I can always check that by foiling, right? First, outer, inner, last. And I think that works. Let me just double check it. So 2x times x would be 2x squared, right? 2x times x. 2x times +1 is plus 2x. -1 times x is -1x. And -1 times +1 is -1. And let's see, does that equal what I want it to? 2x squared. These two inner terms are going to reduce to just plus 1x, and I'm left with the -1. So yes, that does work. Now, by the zero products property, what this says is that either the first product equals 0, so 2x minus 1 equals 0, or I can say that x plus 1 equals 0. And solving each one of these equations gets me my solution. So x is going to equal 1/2, or x is going to equal -1. And as a solution set, I'm going to write these from smallest to largest as -1, 1/2. Now, to solve the trigonometric equation, I'm going to do the same thing. I'm going to subtract 1 from each side, and I'm going to set it equal to 0. So I've got 2 times cosine of x squared. That is the same thing as 2 times cosine squared x plus the cosine of x minus 1 equals 0. And I know that, like I saw above, that this is going to factor to 2 times the cosine of x minus 1 times the cosine of x plus 1. that equals 0. And where this multiplication is happening, I can say that 2 times the cosine of x minus 1 equals 0, or that the cosine of x plus 1 equals 0. So I'm going to get that the cosine of x is equal to 1/2, or that the cosine of x is equal to -1. Okay, so now I'm at the same point that I was with the algebra, 1/2 and -1. I've got 1/2 and -1, but I have to go one step further and actually determine what angle is going to produce each one of these cosines. So what angle produces a cosine of 1/2? That is going to be the measure of pi over 3. That's also going to be the measure of 5 pi over 3. And because there's no limitation as far as 0 to 2 pi, I'm going to say that this is going to be equal to, or going to include plus 2 pi k on the end. For the cosine of x equals -1, the only angle that produces a cosine of -1 is the angle measure of pi. So I'm going to say pi plus 2 pi k. And in both of these cases, don't forget to define k. K is some integer. So from the very beginning, let's just say that part D is what we started with. Keep in mind that what we really have here is 2 times some function squared plus 1 times that same function, but not squared. So we may have been able to say something like, let, I don't know, let r equal the cosine of x. And so then that would have given us 2r squared plus r minus 1 equals 0. And we could have gone through the process of factoring, and then at the very end, gone ahead and substituted that cosine of x back in to actually then solve for the solutions that we got. Part E. Find all possible exact solutions for sine squared x minus cosine squared x minus the sine of x equals 0, where x is in radians and x is between 0 and 2 pi, including 0 but not 2 pi. So whenever you solve any type of equation, it's always helpful if you have the same variable, or in this case, we have a sine squared x and we have a sine of x, but then thrown in is this cosine squared x. What makes trig functions sort of nice is that there's a way to rewrite sine squared x or cosine squared x in terms of the other, and that comes from the Pythagorean identity. Let me remind you that cosine squared x plus sine squared x is equal to 1. So I could solve that Pythagorean identity for cosine squared x to say that this piece right here is equal to, and let me just go ahead and write what's on the left and the right. So I'd have sine squared x minus that cosine squared x, we're going to call 1 minus sine squared x. And again, that's coming from solving the Pythagorean identity for cosine squared x minus the sine of x equals 0. Now that looks super ugly, but let's simplify it, and I think it'll actually end up looking pretty good. So if I distribute this -1 through, then I get sine squared x minus 1 plus sine squared x minus sine of x equals 0. So I've got 2 sine squared x's, and let's see, I'm going to put this in order so that it looks like a quadratic equation. And so I end up with 2 sine squared x minus sine of x minus 1 equals 0. So again, this is a quadratic equation. I'm hoping it factors. If it doesn't, I'd have to use the quadratic formula. I think that this one does factor though. I think that I get 2 times the sine of x, and then I'm going to have sine of x on the other one. And this one I think is going to be a +1 in the first product and a -1 in the second. So I've got 2 times the sine of x plus 1 times sine of x minus 1 equals 0. So I'm going to set each one of these equal to 0. That's going to give me the sine of x equals -1/2. And it's also going to get me the sine of x equals 1. So I'm asking myself, what angle measure for the first one produces a sine of -1/2? And if you've got your unit circle memorized, you know that the answer to that is 7 pi over 6 and 11 pi over 6. And then for the sine of x equals 1, the only angle measure where the sine of an angle equals 1 is up at pi over 2. This one asks me just for the solutions for x between 0 and 2 pi. So I'm going to use set notation, and putting these in order from smallest to largest, I'm going to say pi over 2, I'm going to say 7 pi over 6, and I'm going to say 11 pi over 6. And those are the solutions that came from solving each one of those equations. Part F. Find all possible exact solutions for the tangent of the quantity theta minus pi over 2 equals 1. All right, so I'm going to take the tangent inverse of the left, and I'm going to take tangent inverse of the right. So the tangent inverse undoes the tangent function. I'm left with theta minus pi over 2 is equal to tangent inverse of 1. So what angle measure produces a tangent of 1? And the answer to that is pi over 4. And now I'm going to solve for theta. I'm going to add pi over 2 to each side. So what is pi over 4 plus pi over 2? And I think that that gives me, what does that give me? 3 pi over 4? And this one, there's no limitation. It just says find all the solutions. So hooked onto that 3 pi over 4, I'm going to add multiples of the period, which is pi k, where k is an integer. And just as a reminder, the reason why I only used pi over 4 instead of writing 3 pi over 4 is because I know that I don't have to do that with the tangent function. The sine and cosine have a period of 2 pi. The tangent has a period of pi. So when I take pi over 4 and I add pi to it, I automatically get that 3 pi over 4. So I'm taken care of on that one. All right, part G. Find all possible exact solutions for secant squared x equals 2, where x is in radians and 0 is less than or equal to x is less than 2 pi. Okay, so we're dealing with a secant here. I feel as though I'm probably going to switch that to its reciprocal function, which is 1 over cosine. But before I do that, I'm going to square root both sides so that I make this maybe look a little bit easier and call this the secant of x is equal to plus or minus the square root of 2. Now, secant is the reciprocal of cosine, so I can rewrite this as the cosine of x equals the reciprocal of plus or minus the square root of 2, which is plus or minus 1 over the square root of 2, which is equal to plus or minus square root of 2 over 2. So I am looking for the solutions that have a cosine of not only positive square root of 2 over 2, but also negative square root of 2 over 2. So that's going to give me the solution set of basically all of the multiples of pi over 4 within one rotation of a circle. All right. Part H says to use a graphing device to find all possible solutions rounded to 2 decimal places for x minus 4 times the sine of x equals 0, where theta is in radians. Now, a graphing device is different from just a calculator. We're not asking a calculator to just solve this for us. Here's what we want the calculator, the graphing device, to do. We're going to graph the left-hand side of the function, so x minus 4 times the sine of x, and then we're going to graph the right side of the equation, which is y equals 0. We've seen this technique a few times before. And where the solution for theta lies is at the point of intersection, and it looks like that's happening in 3 locations.